real quick, let's talk about this. Today we're going to be talking about dilations and similarity in the coordinate plane. I'm going to ask you guys, how can you use dilations to draw similar figures on the coordinate plane? We're going to apply similarity properties in the coordinate plane. Use coordinate proof to prove figures are similar. We're going to talk about similar polygons, similar ratio, dilation, and scale factor. Okay, first up, what we got? Figures are similar if they have the same shape, not necessarily the same size. Okay? So what you need to write down, you need to write down this part. Figures that are similar have the same shape, but not necessarily the same size. Okay, give me use your brain here. Is shape 1 and shape 2, are they the same shapes?
Yes.
Yeah. Do they have different sizes?
Yes.
Okay, that means that they're similar. Are shape 1 and shape 2 congruent? No. And if you can understand why they are similar but not congruent, you are about 30% through the course. Seriously. Okay? Congruent means they have the exact same shape and the exact same size. Similar means they have the exact same shape, but they have different sizes. 1 and 3. Is that even the same shape?
No.
No. Even though this is a triangle and this is a triangle, right? This is more of an isosceles triangle. This is a right triangle. Not the same shape. Why? One of the aspects of similarity is that the angles are congruent in both shapes. Okay? If you forget that principle, it's to your dismay. So make sure you got that part down, okay? Everybody with me?
Yes, sir.
Need any more? Let's move on. Oh boy. Two polygons are similar polygons if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. Right? Make sure you write this down. Similar polygons if and only if corresponding angles are congruent, corresponding side lengths are, ooh, big word here, proportional. Okay? First off, when I say corresponding, you kind of, you got to look at what the problem is. Okay? In this example, corresponding means A and E. They are corresponding. B and F. C and G. D and H. Right? Precision matters. Okay? There's a difference in me saying A, B, C, D versus A, C, D, B. Right? A, B, C, D means A, B, C, D. Okay? Why? Because the corresponding angles match up based on the order that they're written. Okay? I can flip E, F, G, H. I could flip it around. Oh, really? Yeah, I could rotate it. I could reflect it. I could translate it somehow. Move it around, right? But if I write it as A, B, C, D, and E, F, G, H, that means that A has to be congruent to E. B has to be congruent to F. C has to be congruent to G. And D has to be congruent to H. Okay? Understand something. Guys, that's just the angles. The lesson is going to be on this part down here. Right? You got me?
Yes, sir.
I expect you to know this. We'll do so many problems that it'll be second nature to you, I think. All right? But don't ever forget that the angles, the corresponding angles are congruent. Right? Everybody got me on that one? Okay. All right. Some of you might need a second or two, so. Yeah, for sure. All right, guys. Check it out. Mr. Hobbs, what's the similarity ratio? Well, let's talk about that. A similarity ratio. The ratio of the lengths of the corresponding sides of two similar polygons. You might as well write this whole slide down, okay? The similarity ratio of triangle ABC to triangle DEF is 3/6. or 1/2. The similarity ratio of triangle DEF to triangle ABC is 6/3 or 2. Question? Just a scratch. Okay. Alright, so let's talk about, because this is, understand something, guys. This is the crux of the lesson right here, okay? We will spend almost all day today talking about what similarity ratios are, what makes polygons similar, things like that, okay? Everybody with me? But understand, I want to make sure you got that down. Here's why. This is what a problem is going to look like. Determine whether the polygons are similar. If so, write the similarity ratio and a similarity statement. This is for rectangles ABCD and EFGH. Okay, let me model this for you. Let me show you how to solve this problem. All right? Right, if I've got ABCD, EFGH, okay, here's what I got to do. I got to break it down. Side AB over side EF. See what I did? Side AB over side EF. The left side of both rectangles. Okay, with me so far? Let's take the top. Side BC over side FG. BC over FG. Okay? That's all I'm doing to start the problem. Just writing down, make sure I get it right. Watch how I do this. A to B over E to F. B to C over F to G. What do you think is going to come next? C to D over G to H. I got it. There you go. C to D over G to H. Okay? Time out. What kind of shape is it? Square. Okay. What do you know about rectangles, Traylon? What do you know about rectangles? They're kind of not squarish. They're rectangular.
They're like.
Let me make it more specific. What about the opposite sides? What are they? Yeah, we call that what in here? Congruent. We say the C word. Congruent. Okay. This is 6. This is 9. This is 4. This is 6. So I see that? Why? Because it's a rectangle. What about it? The opposite sides are congruent. Come on, guys. That was like preschool, right? You know? You knew that in preschool, right? Good. Honest man. Okay? Hard to find. Alright. Hey, the last side down here. Look at it. Last side. I know this is different. I'm going to go D to A, H to E. D to A over H to E. Okay. Have I solved anything yet?
Yeah.
Not a thing. But I've done the most important step, right? Set up my problem. Setting them up proportionally. Because from here, it's child's play, right? Watch this. Daniel, what's the length of AB? 6. Thank you. Traylon, what's the length of EF?
4.
Okay. Watch this. Daniel, what's the length of C to D? Traylon, what's the length of G to H? 4. Cool. Y'all wanna play again? Daniel, what's the length of BC? Good. Traylon, F to G.
6.
All right. Daniel, D to A.
9.
Traylon, H to E.
6.
Cool. Right? You'll see that?
Mm-hmm.
Okay. So here. I want to make sure we see this. If these were congruent rectangles, what would that mean? The sides would be the same, right? So this would be 6 over 6, 9 over 9, right? In that case, it'd be congruent. They're not congruent. Are these fractions? Now listen to me carefully. Are these fractions the same numbers? No. Come on, guys. They're not the same numbers, right? I got a 6 and a 4, the 9 and a 6. But Do these give me the same answer?
Yes.
Ah, what's 9/6? Type in your calculator. In decimal form. What? It ain't 2/3. 3/2, which is the same as what? 1.5. What's 9/6 in your calculator? If you're not doing this, then, I guess you're just like Trevor, right?
6/9.
9/6, guys. It's 3/2, which is 1.5. All right. Hey, listen up. Let's go back to this definition. Similarity ratio is the ratio of the lengths of the corresponding sides of two similar polygons. If my similarity ratio is the same, then I have proportional sides. That word proportional tells me a lot. Okay? Proportional tells me the proportion, meaning fraction or ratio, right, of the bigger side lengths over the smaller side lengths is the same amongst the two different side measures, okay? It would be the same amongst all four of these sides because it's a rectangle, right? We're going to explore that all week. As a matter of fact, I told y'all this, I think, Friday. If I didn't, I'm sorry. This is the biggest unit of the year, right? We're starting it now, late January. I promise you we'll still be doing it in March. Hopefully we'll be done about mid-March, right? So we got to do all similarity proofs. We got to do congruency, triangle congruency, congruent triangles, congruent triangle proofs, and then we got to do different polygons and parallelograms, okay? Whole bunch of stuff. This is just day one, all right? You'll see that if you get this point, you get similarity, right? This tells me that they're not congruent. This tells me that they're similar, though. Okay? I wanted to do the angles. Angle A would match up with what angle? A and E. B would match up with F, C, and D, and that's so elementary, okay? Right? By the way, let's see. But don't miss that step, okay? The angles have to be congruent. The sides are proportional. If it's a rectangle, all the angles are how much? 90 degrees. They're all right angles, right? So here it is, just in case you didn't believe me, all right? All the congruent angles, they're all right angles. They're all congruent. All the sides, 3/2, 3/2, 3/2, 3/2, right? Every single one of these sides is 3/2. One last part that I forgot. I'm only going to do this one time, so make sure you write it down. Last part of this. Understand, this said write the similarity ratio. If I get that, that's what I put in the box. So if you need the help with that, here is my similarity ratio. Okay? That's what that is. The similarity ratio. I can ask it in fraction form or decimal form. All right? Y'all hear me? Okay? Either one. That's why I got both of them in there. I also asked for a what? Similarity statement. Okay? I'll do this one time. All right? It's going to kill you. Here we go. Rectangle A, B, C, D is similar to, that squiggly thing means similar. It's similar to rectangle E, F, G, H. One time. I know. Wow, right? Wow. Mr. Hobbs, how'd you get that? I looked right here. Right? That's all you got to look at for your similarity statement. Soon we'll write a congruent statement. Guess what it would look like? That. Except, you know what the congruent symbol is?
Being an equal sign.
Yeah, with a similarity squiggly over it, okay? Got me? This is congruent, right? Because guess what? Conveniently, not only are they equal, they're also similar, right? I said if they were all one, if they all had the same length, they'd be similar. They'd all have one, okay? That would be a congruency symbol. Here is the similarities, okay? All right, if you drew a square, it's okay. We'll teach you rectangles later in the semester, all right? All right, then we got to the good stuff. A dilation is a transformation that changes the size of a figure, but not its shape. Pre-image and the image are always similar. A scale factor describes how much the figure is enlarged or reduced. I want you to write that part down, okay? Then it goes on, it says dilation with scale factor k, you find the image of a point by multiplying each coordinate by k. Okay, write down the helpful hint as well. If the scale factor of a dilation is greater than 1, it is an enlargement. If the scale factor is less than 1, it's a reduction. Right? Write all that down for me, please. Real quick. Hey, dilation. All right, this is kind of interesting, right? It changes the size of a figure, but not its shape. Meaning that when I apply a scale factor, it makes a figure enlarged or reduced, right? Enlarged. Tell me a non-mathematical way of saying that. Bigger. Reduced. Smaller, right? Bigger or smaller. I think you guys get a full understanding of this. All right. If I have a scale factor that is between 0 and 1, anything between 0 and 1, what's happening to my figure? It's shrinking. It's reducing, right? That's a reduction. Okay? That is a reduction. If I have a scale factor that is bigger than 1, anything bigger than 1, what's happening to it? It's enlarging, right? That's an enlargement with an E. Okay? All right. What if my scale factor was 1? It's the same. And what do we call that? Congruent. Right? If the scale factor is 1, that means that my figures are congruent figures. Right? Okay? So, are congruent figures similar figures? Yes, absolutely. They just don't have any really special properties that other similarity figures do, other than the fact that they're still proportional. They just have a scale factor of 1, okay? All right? We don't teach things that way, because if all I had you guys doing was multiplying everything by 1 all the time, you'd be like him, asleep most of the time, all right? Oh, sorry, harsh? All right. What's it going to look like, Mr. Hobbs? I'll tell you, like this. Draw the border of the photo after a dilation with a scale factor of 5 over 2. Time out. 5 over 2. Bigger than 1 or smaller than 1?
No. Bigger.
Bigger than 1. Correct? 5 over 2 is bigger than 1. Yeah, it's 2.5, okay? I would take each of the coordinate points, multiply all of them by 5 over 2. My scale factor is 5 over 2. Multiply 0, 0 times 5 over 2. 0 times 5 over 2 is 0. 0 times 5 over 2 is 0. Nothing happened to point A, did it? It stays the same, okay? The other points, however, are all going to get bigger. Okay? Everything's going to get bigger. 0, 4, 3, 4, 3, 0. Y'all see what you do with your scale factor? It's really simple multiplication is all it is, okay? Got me? It's just multiplying something by coordinate points. Okay? Alright, I plot the new points and draw the new rectangle. Why don't you guys do this one? Okay? I want you all to figure this one out. Draw the border of the original photo after a dilation with a scale factor of 1/2. Okay, go ahead, get started on this. I'm going to give you a couple minutes to type. How do we get this problem going? Here's how. Start off by writing the original coordinate points for everything. 0, 0, 0, 4, 3, 4, 3, 0. Multiply each of the coordinate points by your scale factor. Everything gets multiplied by 1/2. Okay? 1/2 times 0 is still what? 0. So the first point never changed, right? It was 0, 0. Okay? 1/2 of 4 is 2. 1/2 of 3, 1.5. Right? So that's how I'm getting these other points. B prime is at 0, 2. C prime is at 1.5, 2. D prime is at 1.5, 0. All right? Got me? All right. If you set this problem up like this, 2 over 4, 1.5 over 3, and you reduced all those fractions like we started with. Remember that? I started with a triangle with lengths. And I set all those problems up and said, find your similarity ratio. Guess what our similarity ratio would be here? 1/2, right? Got me? Okay, that's the whole concept. We got to tie all of those loose ends up. Okay? Then what would I do? I'd plot it. Okay? And I could see in a coordinate plane the reduction that takes place in that particular rectangle. Okay, one last thing that you're gonna see today. I want to make sure I go over it before I get you on your classwork. Here we go. Given that triangle TUO is similar to triangle RSO, time out. If the triangles are similar, the sides are what? Not congruent. Not corresponding. The P word. Proportional. Got it? We got congruent. We got proportional. These are proportional. Okay? Find the coordinates of U and the scale factor. Okay. Y'all ready for this? Since TUO is similar to RSO, that means that, check it out, RO over TO is the same as SO over UO. Yo? Alright? How far is it from O to R? Listen to how I said the question. How far is it from O to R?
-4.
How you going to measure distance in negative numbers?
Oh.
It's absolute value. You took the... Got it, okay? Yeah, it's 12 units, correct? It's 12 units from O to R. I know it says -12. I know the guy who wrote the problem, okay? He's a nice guy, right? But it's 12 units. Remember, distance is never going to be measured in negative values, right? Don't talk about it being negative miles to Atlanta. Say it's 58 miles to Atlanta, okay? So that's how I get these numbers right here. 12 over 9 is the same as 16 over, and this is my x, okay? That's my x. Guys, when y'all see this, what are you going to do? Say what? Cross, multiply. Crisscross applesauce, multiply them across. Whatever that meant, all right? Don't multiply them across. You cross multiply. 12 times x, 16 times 9. 12x equals 144. Divide 12 by both sides. X equals 12. Okay, great. So this is at 0, 12. I want to find a scale factor now. Okay? How did I go from, either how did I go from S to U, or how did I go up? In this case, I think they're asking how did you go down? Okay? 12 over 16 should be the same as 9 over 12 should be the same as 3/4. The scale factor that got me down was 3/4. Okay? A lot of math in there, I know. Some cross multiplication. You might have to dust some cobwebs off. But that's what we got today.